So here we go on the math section. I've written the two equations up here. I actually started doing this problem and redid the video because I made a math error. So we have two equations. C is equal to wavelength times frequency. We have energy is equal to H, which is a Planck's constant, times the frequency. Notice the numerical values are on your handout. The radio wave from a local radio station has a wavelength. That's this symbol. Oh, it's that symbol. 3.16 meters. So we want to find out what the frequency is. What are the numbers on the dial? And it's an FM station, and FM stations express their frequency in megahertz. AM stations use kilohertz, just FYI. All right, so we're going to use the equation that has wavelength in it. So I wrote that down. Pick the constant C, which is the number just like pi. Put the 3.16 in that we have for wavelength, and frequency was just a variable. So to solve for that variable, we divide both sides by the 3.16. So then I was doing the math here. So the way you do that is you type in 3 on the calculator. Remember how we use that times 10 to the whatever button. So it's 3 exp to the 8th. And we're going to divide by 3.16. And that gives me a syntax error. I don't know why, so let's try that again. So 3 exp to the 8th divided by 3.16. That looks good. Okay, so that gives me 94.9. You can see the decimal point right over here. Now you can't see the decimal. Now you can, right there. So I have to count over. So I got from this point, make sure you can see it, from this point here, 1, 2, 3, 4, 5, 6, 7. So it is 9.49 times 10 to the 7th. And the unit on that, since that's meters per second, that's meters over 1, it's 1 over seconds. So that's 9.49 times 10 to the 7th reciprocal seconds, but a reciprocal second is also called a hertz. So then we need to change that into megahertz. So we put hertz on the bottom. We put megahertz on the top. Mega means million. So one of these is a million of those. So you'd have 9.49 times 10 to the 7th divided by 1 times 10 to the 6th. So really that's going to be 94.9 megahertz, and that's what it would say on the FM dial. It's pretty close to KC 95, but it's not. I don't know if there is a 94.7 here in St. Louis. Okay, next question. You have a photon with this energy of 3 times 10 to the 3.16 times 10 to the negative 19th. What's its wavelength? Well, we know energy is equal to H times frequency. Pen's about to run out of ink. We'll just change pens here. So energy is equal to H times frequency. Green's a nice color. So, and that's a sophomore color for homecoming. So E is equal to H nu, so we know the E is 3.16 times 10 to the negative 19th joules. We know that H is 6.63 times 10 to the negative 34th joules per hertz. We don't know frequency, but we don't really want frequency. What do we want? We want wavelength. So to solve for wavelength, I guess we could do this. We could say that C is equal to wavelength times frequency, and then we could rearrange this. What if I wanted to get that, solve for that? Couldn't I just divide both sides by wavelength? So then I'd have C divided by wavelength is equal to frequency. So let's just plug that in. Instead of nu, why don't we just say that's C over wavelength? So C over wavelength. So now we need to solve for wavelength. So we multiply both sides by wavelength. So now I have the wavelength multiplied by 3, it's a weird 3, 3.16 times 10 to the negative 19th joules equals 6.63 times 10 to the negative 34th joules per hertz multiplied by 3.00 times 10 to the 8th meters per second. Now remember, this number here is that constant that's up here, so I just plugged it in. So now you divide both sides by the 3.16 times 10 to the negative 19th joules. And that'll give us our final answer in meters. We'll talk in a minute about why it's in meters. Okay, so let's do the math. So 6. I'm trying to get so you can see my calculator here. My light's kind of weird because I'm taking these numbers as 6.63 exp negative 34th multiplied by 3 exp to the 8th equals divided by 3.16 exp to the negative 19th. And I get 6.29 times 10 to the negative 7th. We'll just call it 6.29 times 10 to the negative 7th. So that's our answer. And then the actual unit cancellation, you can tell joules cancel out here. On this side, a joule is the same thing as a Newton. Well, we don't need to get into that actually. We can just use a hertz is a 1 over second. So we could get rid of that, put 1 over seconds. Then if you have joules divided by 1 over seconds, you know that when you divide fractions, you multiply by the reciprocal. So you would end up with a joules times second over 1. So I'm going to write down up here without writing down. So we'd have a joule second times meters per second. And that would be all divided by joules on the bottom right here. So you see seconds cancel, joules cancel, and you're left with just plain old meters. All right, that's the units. All right, now this next question is about the duck. And it's the things you've been wondering about. You know, we had this little equation that the wavelength of a particle, this was de Broglie's equation, is equal to h divided by mass times velocity. So that was the equation that we had. We know that h is 6.63 times 10 to the negative 34th joules per hertz. We know that the mass is 2.1 kilograms. And we know that the velocity is 3.00 meters per second. Now this is not your speed of light, 3.00. This is just a duck flying. But the equation, or the speed is, you still use the 3.00, not the 3.00 times 10 to the 8th, what I'm trying to say. So I'm going to go ahead and do this one. You won't be able to see, but I'm just doing 6.63 exp negative 34th multiplying by 1 because I don't need to do anything. It's just that number. Then I'm going to divide by 2.1, then divide again by 3.00, which is really just 3 on the calculator as far as the calculator is concerned. So our wavelength of a duck is 1.05 times 10 to the negative 34th. It's got a little negative 34th right there. Meters, which is not very big. So that's why we don't worry about the wavelength of a duck, but it's good to have it resolved in your mind, I'm sure. So you may be thinking, how in the world did you get meters out of all this unit mess? So just in case you're wondering that, you have joules per hertz divided by kilogram meters over seconds. See, kilogram meters seconds. So we'll do the unit cancellation real quick. Multiplied by the reciprocal, so that would be the same thing as joules per hertz multiplied by seconds over kilogram meters. So far so good. Just flipping the bottom. So now maybe we can say we know a joule is a Newton meter. We talked about that earlier. It's a unit of work. So Newton meters seconds over hertz kilogram meters. Oh look, meters cancel. That's nice. So now we have Newton's seconds over hertz. But a hertz a 1 over second in it. So really that's the same thing as a Newton second 1 over second kilograms. Well, again, we've got a fraction now, so we're going to multiply by the reciprocal. So now we've got Newton second squared over kilogram. So So you flip the second up on top and the kilogram will be down there. So you're just flipping the bottom. Okay, about a Newton is a unit of force. So I'm going to come up here. So a Newton is a unit of force, and a force was a kilogram meter per second squared. You remember that from physics. And that's multiplied by seconds squared. Right here. And that's divided by kilograms. So then, seconds squareds cancel. Now you have kilogram meters over kilograms. Oh, look, kilograms cancel. So your final unit is meters. So that's how you do the unit cancellation. And I'll stop here and then make one more video of the last one.